So I'm going to talk about how to make sense of interpretations of quantum physics using pictures. So here's the plan. I'll motivate quantum physics as a process theory, give an overview of categorical quantum mechanics, which is a process theory for quantum physics, and its diagrammatic formalism. And then I'll try to make sense of some prevailing interpretations of quantum mechanics in this framework. But what about the measurement problem? The measurement problem has always received a lot of attention in quantum foundations. Many alternative formulations and interpretations of quantum theory have been proposed, trying to solve the measurement problem. But these formulations and interpretations treat quantum states and measurement as the first-class citizens. However, there's an alternative. Rather than defining individuals or particles or waves or wave functions, and then attempting to describe measurement, one can start by defining how objects compose and develop quantum theory from a compositional lens, as argued by Schrödinger. Here's a famous quote by Schrödinger where he's emphasizing the primacy of composition or interaction or entanglement. He says, "I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought." And okay, so from now on, I'll talk a bit about process theory, what a process theory is, and then we'll try formulating a process theory for quantum physics. So process theory is one way to describe compositional theories, and formally we can define it like this. It consists of systems or types or interfaces, and we represent these types or systems by wires. And it also includes a collection of processes which are represented by boxes, and where each process has a number of input and output wires. But that's not sufficient. There also has to be a means of composing processes, which is represented by wiring these boxes together. And the process that you get as a result should also be part of the set of the processes. So the set of processes is closed. Categorical quantum mechanics is a process theoretic incarnation of quantum theory. There are a number of ways to think of CQM. Initially, it was conceived of as a high-level language on top of Hilbert space. So you can think of it as Python or some other high-level programming language, and the analog of machine code would be Hilbert space. But recently, there has been a reconstruction theorem, according to which you can think of CQM as a reconstruction of quantum mechanics. Thirdly, there is an equivalence between these diagrams and categories. So CQM originally is a category theoretic formulation, and because it is a certain kind of category theory, you can have diagrams, and these diagrams can be used as a graphical substitute for Hilbert space. But most importantly, it foregrounds composition and interaction of quantum processes. So the idea of taking processes rather than states or individuals as first-class citizens goes back to the pre-Socratic philosopher Heraclitus and was rekindled by Whitehead in Process and Reality in the previous century. So let's try motivating a definition of what a process is. It's diagrammatically, it's a box which has a number of input and output wires. You can think of these wires as inputs and these as outputs. There can be 0 or more inputs, 0 or more outputs, and processes can be composed. Now, in Whitehead, processes can be composed in sequence. So if you have n processes, you can compose them like this. And for this process theory to be interesting, there has to be a non-trivial composition, which means that not all the processes should be separable like this. Because if all the processes are separable like this, then the theory is not interesting, right? Because whatever you plug in as the input, you'll get the same output at the end. So this is not a very interesting theory. So there has to be some interesting process, which is not separable. But Whitehead, so you can think of it as sequential composition. Whitehead did not explicitly have parallel composition. And then comes Schrodinger. He says entanglement is not one, but rather the characteristic trait of quantum mechanics. And typical example is that you can have a state which is not separable. And this you can think of it as non-trivial parallel composition. So Whitehead and Schrodinger together give us series and parallel composition. You can also think of parallel composition as saying like you have a process along with another process. So these two processes can be thought of as happening at the same time. Whereas in Whitehead, the processes are ordered in time. There's first process 1 and then process 2. Okay, now when we start composing these processes, we get diagrams. And these wires are labeled because when you define a process, you have to say what is the input, what is the output. And these inputs and outputs should match. So from now onwards, in my talk, think of time as flowing from bottom to top. So this is, this process happens first. These are parallel processes, then this process happens, and then these are the outputs. So this is the input of the overall diagram. These are the outputs. So in diagrams, only connectivity matters. So these two diagrams are equal. You can see that all the connections are the same. This G is connected to H. H is connected to G and K. So the connectivity stays the same, and the order of these input and output wires of the overall diagram stays the same. So I've already stated it before. When you are composing processes, the types should match. So if you have these two processes, you can compose them like this. The types are matching. This is not allowed because these types don't match. So in short, a process theory is a collection of processes which it makes sense to compose. Now we start building some components of the quantum theory. We can describe states as processes with no input. Like I said, input is, you can think of input at the bottom and output at the top. So this is, you can think of it as a preparation of state, where we don't worry about what's happening before the preparation. Then as its dual, we have effects or tests. These are processes with no output. And then you can think of numbers as processes with no input and no output. This is how you can represent a number. And when you compose a state and an effect, you get a number. So here's a state, here's a test, we have composed, you get a number, you can think of it as a probability. And this is what we call the generalized Born rule. Now, already with this much theoretical apparatus, we can start looking at the effects of separability, which I already hinted in the previous slides. So if a process is circle separable, which means separable in time, then it can be expressed in terms of a state and effect. But this is not interesting. When this process is applied to any state, for example, state psi, this is equal to this because the process is separable. And this is just a number. And you get the same state. So if you have a separable process, no matter which input you apply, you always get the same output up to a scalar. So if all the processes in a process theory are circle separable, then the theory is trivial. Now, we can think of separability in space as well, or as two processes happening at the same time. So we can, first of all, we can define states for one or more than one systems. A two-system state is called tensor separable if it can be expressed in terms of two one-state systems, like this. States that are not separable are called non-separable states, of course. And there is a completely non-separable state, which we represent as a cup. You can think of it as a Bell state. And its dual is like a Bell test. This is how we represent it. Now, there's a very nice theorem which says that if a process theory has cup states for every type, meaning that for any system, you can make a cup state, and in which every state is separable, it has trivial dynamics. This is very similar to what we saw here. So this means that we need to have non-trivial series and parallel composition for non-trivial dynamics in the theory. But this is not sufficient for quantum theory. We need some notion of conjugates, adjoints, transpose. This is how you can have a slanting edge at one side of the box, and then you can define a conjugate like this. This is a horizontally flipped version. You can also define a transpose, changing the inputs and outputs. So this is like taking a box and rotating it. And if you take the transpose and then the conjugate, you get the adjoint. So these are the different kinds of processes that we know in quantum theory. Okay, as a first attempt, we can try formulating a quantum theory as a process theory of linear maps. So in this process theory, systems are Hilbert spaces, processes are complex linear maps. But there's a problem. The numbers in this theory are complex numbers. If you have, if there's some complex number in this state and you take a test, you may get a complex probability, which is not allowed. So this means that we need to revise our notion of numbers. We can do it by multiplying this number with its conjugate, and we get the usual Bond rule. But now this is not the same process theory anymore, because the states and tests were defined. In some sense, the states and tests are defined in terms of each other. So the number and these states and effects are defined. They have to be compositional. So we need to build a new process theory with double states, double effects, doubled numbers. So, you can just multiply everything with its conjugate and you get a double process theory. So this is the state, this is the test, and you get that usual Bond rule. So the wires are also doubled Hilbert space, the processes are doubled. So you can think of this, you can use a thicker wire to represent these doubled wires and doubled processes. This is what is inside the double box. Now, the good thing about doubling is that it preserves the diagram. So if you have a diagram and if you double the process theory, the diagram stays the same. It looks the same. But it does not preserve global phases. So if there were a phase, a complex phase here, and you take its conjugate, the phase disappears. So the global phases are not preserved. Now, in this process theory, we can also have a notion of discarding. So discarding means getting rid of a state or destroying a state. And we use this symbol for discarding, and discarding is essentially like short circuiting. So you take the two individual wires inside the double wire and you connect these. And you can already see that this is in some sense like the cap test which we saw here. This is the cap test. Now, discarding operation gets rid of a state. We can see it mathematically. You take a state, you discard it. So inside this double state, we have two states and they are connected. In the diagrams, only connectivity matters, so you can move it like this, and essentially you get this. And because we assume the states to be normalized, this is the number 1, which we represent as an empty box. Okay, so now we have a process theory of quantum maps. This process theory includes double Hilbert spaces as system types, and the diagrams are made of pure quantum maps, which are these double maps, and discarding. Discarding is not a pure quantum map. And we can also impose causality on the theory. So a process is causal if it obeys this equation. This equation means that if you apply any quantum process, it can be a unitary map, and then you discard the state, this is operationally equal to just discarding the state. So this process doesn't matter. So if we impose this condition, we get a process theory of causal quantum maps. Okay, so far so good. But what about classical systems? We also need to have some notion of classicality in the theory from an operational perspective. And we can develop it like this. So if you have a single state without doubling, this is essentially preparing the classical system in value I. You can have its dual, which is testing testing whether the system is in value I. And you can describe an orthonormal basis. If I and j are equal, you get 1, otherwise 0. Now, the general state of a classical system is given by this probability distribution. These are the probabilities of the system being in these states. Unlike quantum systems, classical systems can also be copied. This is a copy operation. So you can think of it like this. If you apply this state here, you get 2 copies out. And there's also the delete process, which is the classical equivalent of discarding. Okay, now, what about classical quantum interaction? So, like I said, the quantum systems are doubled, classical are undoubled. These wires are not equal. There needs to be some kind of process relating these wires. And these processes are encode and measure. If you have a classical system, and you have a process which gives a quantum system, this is encode. So this is how we represent the encode operation. And you can think of it like making a copy of a classical system. So if you have 2 copies, this means that these 2 wires are equal to this double wire. So you can take a classical probability distribution for a classical system, and then you can copy it to get a maximally mixed state. Its dual is measure, which is you have 2 wires going in, 1 wire going out. Now, these diagrams may look ad hoc, but there are mathematical definitions of these, which I haven't shown here because they are not really the point of this talk. You can think of decoherence as first apply measure and then encode. So when you apply the measurement operation, the off-diagonal terms in the density matrix are lost. And whatever you get can be thought of as a classical probability distribution. And then you copy or encode the state. So you get a density matrix for a classical state. Now we have a new process theory, which is a process theory of quantum classical maps. And the system types are double wires and single wires for quantum and classical systems, respectively. And the diagrams are made of these processes. These are the pure quantum maps. This is encode. This is measure. So quantum processes are classical quantum maps, which we can represent like this generally, which are causal. So by causality, again, we mean that if we discard these outcomes, this process doesn't matter. So the theory of quantum processes is what we claim to be quantum theory from an informational or operationalist perspective. And in this theory, you can have like sub-theories. So you can have, if a quantum process has no classical input, no classical output, you get a totally quantum process. If there are no quantum inputs and outputs represented like this, you get classical processes. Okay, now we can talk a bit about measurement, which is the main focus of this talk. So we have already seen an instance of measurement, which is a process that transforms these 2 wires into a single wire. But this is very specific. We can have a more general notion. For example, we can have a demolition orthonormal basis measurement like this, where this U is a unitary. So you can think of it as changing the base in which you want to, changing the basis of the measurement. So a non-demolition measurement is represented like this. So when you have made the measurement, this is the quantum state, and this is the outcome which we can check. This is a classical outcome. Now, if we discard this quantum state like this, then we get a demolition measurement, which is expected. So this discarding operation is equal to this. Now, in this diagrammatic formalism, there are some rewrite rules which I haven't shown here. But using those rewrite rules, we can simplify these diagrams or rewrite these diagrams. So this discarding is equal to this dot. And you can rewrite this whole diagram like this, which is essentially the definition of demolition measurement. On the contrary, if we discard this classical outcome, which you do like this, then you can show that this is equal to decoherence. Remember that in decoherence, we first apply a measurement and then encode. More generally, if you want to include a general basis, then non-demolition measurement looks like this, where U is a unitary. Okay, now let's see what happens if you measure a quantum state, rho, and the outcome is, let's say, I. So I've made a measurement, and on my screen, on my measurement device, I can see an outcome I, which is a classical outcome. So I plug in this outcome here, and then the rewrite rules tell me that I get this. So this is a number, this is the probability. Again, this is an application of the Bond rule, and this is the outgoing state. So the measurement results in what is usually called a collapse. I started out with this state, I've applied a measurement, I got this state. Okay, now we try to look at textbook quantum mechanics in this formalism. Textbook quantum mechanics is represented as a recipe, as we all know, and I'm going to draw this recipe. So quantum system is a state in the Hilbert space. This is a quantum state. I can show that this is, I can have like a set theoretic notation here if I like. In the absence of measurement, the state evolves via a unitary evolution like this. So if I want to represent a state that is evolving, I have this state plugged in here. When I apply a measurement, this is the Bond rule. This gives me a number, and this is the outcome that I get. And if I focus just on this part of the diagram, this is just the probability of finding the state in phi. So the state was prepared in psi. There was unitary evolution, and then it was found to be in phi. So this is the probability. If I have a composite of two systems, this is given by tensor product, which diagrammatically looks like this. So not very illuminating, but it becomes more fun if we start looking at Einstein-Podolsky-Rosen scenarios. So say there are two parties, Alice and Bob, they share an entangled state, one of the Bell states. So this is a maximally entangled state. Diagrammatically, we represent it as a double cup. So in all these diagrams, I'm assuming Alice to be at the left-hand side and Bob to be at the right-hand side. And you can think of this separation to be the separation in space. Okay, Alice and Bob can change the measurement basis if they like, so they can apply some unitary or POVM operators here. And then Alice decides to discard her state. So this is the discarding operation. Remember that we are working in a causal theory, so this means that once I've discarded this state here, this operation doesn't matter, so this is equal to this diagram. And in the diagram, only connectivity matters. There's only one output in this diagram. This output has been destroyed. There's only one output. So I can rewrite it like this. I've unbent the wire. And once again, I apply the causality postulate, but in reverse. So this means that if Alice discards her state, this means that Bob is going to get a maximally mixed state. Now, this is not controversial. We know this from standard quantum mechanics. Now, we may ask, what is the probability of Alice and Bob measuring the states psi1 and psi2? This is how you get it. So in this scenario, I haven't applied the change of basis. I've just applied these effects. I can rewrite it like this. This gives me the joint probability. And assuming that we started with the Bell state, this will give me 1 if these states are the same. This will give me 0 if these are orthogonal. More generally, the probabilities are given by this diagram, in which I have also applied the change of basis. And more generally, even more generally, you can think of demolition measurements in the EPR scenario like this. Here's Alice making a demolition measurement, Bob making a demolition measurement. And if you want to do something with this classical outcome. You can, apply some operations here. Maybe you want to copy it, or maybe you want to discard it, whatever you like. But it becomes more interesting if we have non-demolition measurements. So non-demolition measurements, in non-demolition measurements, you have the quantum state, but also the classical outcome. So say that Alice and Bob have made the measurement, and Alice decides to destroy the measurement outcome that she had, or she forgets it. So this is how you have delete operation in classical systems. Now I apply some rewrite rules. I fuse these two dots. Then I unfuse this dot into two dots, and I get decoherence at Alice's side. Now we can ask what happens at Bob's side, or does it affect Bob? Now we can also move these boxes, slide these boxes along these wires. So I slide this box to Bob's side, and I get this diagram. And then I can also slide these dots. So now, how do you make sense of this diagram? This is a classical correlation, and one part of this two-party classical system is copied at Alice's side, and one part is copied at Bob's side. So if Alice gets rid of her measurement, we get decoherence, and this decoherence affects both the parties. So you get like a classically correlated system as a result of non-demolition measurement followed by destroying Alice's information. More generally, you have decoherence at both sides. But decoherence is also because of environment, right? So decoherence is also defined as the environment that is creating some noise or playing some role. So you can think of it as a unitary evolution if you are outside that environment. So this is the ready state of the environment. This is the state. This is a single quantum state. There is a unitary interaction, and then because of the noise, there is environmental decoherence. Now I can rewrite this diagram like this. I'm going to pull this wire, bend it twice, and get this diagram. Now again, this is similar to the Alice and Bob situation where Alice forgot or destroyed her information. So we have a classical correlation between the environment and the quantum state. And this whole sub-diagram can be thought of as a process applied to the quantum state. If the information that is in the environment gets destroyed, then this means that the original quantum state is in the maximally mixed state. Okay, so there's an interpretation of quantum mechanics called relational quantum mechanics due to Rovelli, and in this interpretation, every measurement is with respect to an observer, and it doesn't have to be a conscious observer. It can be a particle. It can be anything that interacts. So it can be a particle. It can be, say, a photon, an electron. So now we are looking at the EPR Bell scenario in relational quantum mechanics. So if you have two parties, Alice and Bob, and if you want to consider what happens to their states, to their parts of the entangled state, then you need to have, if you want to have like a complete description or a holistic description, you need to have a third observer, which I haven't shown in this diagram. Let's say this observer is Wigner. Now Alice and Bob perform their measurements. This is Alice's measurement device in the ready state. This is Bob's device in the ready state. They apply a measurement. With respect to Wigner, this is a unitary interaction. These indices are important, otherwise these operations don't make sense in relational quantum mechanics, and we get so as a result of this measurement, these two states get entangled and these two states get entangled. Now, Wigner may try to interact with Alice and Bob to find out the measurement outcomes they have obtained. So for Wigner, this would look like this. The original state is destroyed, and for Wigner, the quantum state becomes a classical outcome. But this is not the whole part of the story of relational quantum mechanics. There are other perspectives as well. There is Alice's perspective, for example. So for Alice, Bob's state and the part of the entangled state which Bob measured get entangled. And Alice's state gives a classical outcome. So this is Alice's perspective. And now Alice may want to interact with Bob to find out Bob's outcome. This is what it looks like this. Now we can ask the question, why does Alice need to interact with Bob, or why does Wigner need to interact with Alice and Bob? It is important because otherwise you can't really make sense of the correlations. You need a third observer, or you need one of the observers to interact with the other observer to make sense of the correlations. Now let's talk a bit about Everettian quantum mechanics. So there are a number of ways to have diagrammatic versions of Everettian quantum mechanics. So the naive one is branching worlds, in which you need to have some additional structure which is not there in our process theory. This is the direct sum or a byproduct. This is not part of our theory, so I'm not going to talk too much about it. But you can have the universal wave function perspective, in which both the parties or their measurement devices get entangled with the states, with the respective states. Now, notice that this looks very similar to Wigner's perspective in relational quantum mechanics. The only difference is that in Wigner's perspective, there are these indices. So in Wigner's perspective, these are like, some people may call that these are potential processes, not actual processes, until Wigner interacts. Whereas in Everettian quantum mechanics, these are thought to be actual processes that are happening. But even in Everettian quantum mechanics, we have these different perspectives. There's a universal wave function perspective, there's Alice's perspective, in which the diagram looks slightly different, there's a Bob's perspective. So the main difference between Everettian quantum mechanics and relational quantum mechanics seem to be difference in ontology. Structurally, they are the same, and it is expected because both of these interpretations are drawing their inspiration from the same paper by Hugh Everett. Now we can look at hidden variable perspectives as well. I don't understand superdeterministic theories very well, but this is a very naive version where instead of having an entangled quantum state, I have a classical correlation plus a hidden variable, and the rest of the measurement looks the same. This needs to be developed a bit more. But yesterday I was thinking of Bohmian quantum mechanics. So in Bohmian mechanics, we have a pilot wave. Again, this is my naive reading of Bohmian mechanics. If people object to this, I'm happy to talk and learn more. So in Bohmian mechanics, we have this pilot wave, and these are particles which have classical trajectories. Now in Bohmian mechanics, this pilot wave directs the trajectory of these particles. So before any measurement and after every measurement, there needs to be this interaction, which are these rectangular boxes between the particles and the pilot wave. And this is Alice and Bob making their change in basis, and these are the outcomes. Now, you can think of Bohmian mechanics in two ways. I can think of this whole sub-diagram, this triangular sub-diagram, as the state, as a complete description of the state, which is the pilot wave plus the particles. And these dashed boxes can be thought of as measurements in Bohmian mechanics. So in this version, the hidden variables are essentially in the state. But I can make a different version where, so these two diagrams are the same, I've just moved some of these boxes upwards. I can have so in this arrangement, I'm emphasizing the pilot wave to be the main, to be the essential part of the state, and all the hidden variables are within the measurement. So this is similar to the hidden measurement interpretations of quantum mechanics. And Okay, so this was a survey of some interpretations in categorical quantum mechanics. And the emphasis is on composition, or how interaction takes place. The diagrammatic representations clearly reflect the varied levels of complexity of structure involved in these interpretations. These structural relationships between the different interpretations may be of interest to the structural realist. I myself lean towards structural realism, so I like the fact that you can have the same mathematical machinery and interpret it in different ways. And essentially, the structure is the same. The mathematical structure is the same, so that is very attractive to me. This is very much a work in progress. There are many open questions, and I'll state these here. So far, we have looked at the aesthetic relationships between the different interpretations. So I would like to make it more formal, mathematically and conceptually. And then we can ask the question, which is the most natural interpretation from a compositional point of view, or a process theoretic point of view? And finally, can we develop an ontology of quantum physics which foregrounds process ontology rather than object ontology? Thank you very much.
Thanks, Hamza.
I'm happy to take questions.
Do I speak into this or just put it near me? Could you go to the slide where you introduced the classical cloning circuit or process?
Yeah, I can.
I just have a rather broad philosophical remark to make that hadn't struck me before seeing your talk. And that is, so presumably you don't have this copy in the quantum case.
Yeah.
But you say you do classically. It struck me for the first time that implicit in that dichotomy is a comparison between quantum states and classical ontic states. Classical ontic states can be copied, they can be cloned. Quantum states cannot be cloned. But if you were talking about classical epistemic states, in other words, probability distributions, they can't be cloned either. So I'm just saying, I don't know of what value this is, we can discuss it later. But for the first time, it struck me that implicit in all of this discussion is effectively a treatment of quantum states as being ontic rather than epistemic. Simply because you're making the distinction that you don't have the copy diagram in the quantum case. And I'd say, well, you don't have it in the classical case either, as long as you're talking about epistemic states.
Well, these diagrams don't really distinguish between epistemic and, I mean, essentially all the diagrams that I showed you can be thought of as ontic or epistemic.
No, I disagree. I disagree because you would not have the copy in classical physics if you're talking about epistemic states. There's a classical no-cloning theorem for epistemic states.
Okay, I'm happy to discuss it.
So implicit in that is that you're talking about an ontic state.
Okay. Yeah, we can talk a bit more about that.
I just have a small clarificatory question and then a slightly more substantial one.
Yeah.
So the small clarificatory one is, I think, maybe a little bit earlier you mentioned that the maps you're using are linear maps. I'm just wondering, so is that the only requirement you're imposing? Like,
No. So this we discarded this theory right when we saw that it doesn't give us the Born rule. So in the more general quantum process theory, we have POVM maps.
And I guess the second one, I guess it's very similar to Chris's question. So maybe it's the same question. So like the two examples you gave are hidden variable theories, which is obviously an ontic interpretation.
Yeah.
The relational interpretation is not really ontic in that sense, but observers are not really special there, right?
Yeah.
It could be anything.
Yeah, that's right. Yeah, that's
so like,
right.
how do you make sense of an interpretation where the observer plays a more important role?
Yeah, so what I haven't shown in this talk is a definition of what we mean by, I mean, you may have seen a mention of the word compositionality somewhere, right? Or compositional. So the way we describe compositional is that you have parts that you can compose, and there has to be some non-trivial composition, right? Like classical correlation or entanglement. And each part, whether it is a subsystem or a bigger system, has to have correspondence with some ontology. So to link to Chris's point, we are assuming that all the theories are ontological, which is why we haven't explicitly mentioned cubism and other epistemic theories. Yeah.
Thanks for the talk. I very much enjoyed it. Can you go back to the slide on Bohmian mechanics?
Yeah, I was expecting that.
Because I think there is another problem with this dichotomy of classical and quantum states. Right, this one, the one before, or this one. So you denote with thin lines classical states and thick.
That's right. Yeah, that's right. That's right.
States, quantum states. Now I think the other problem that you have is here that the preparation of these ontic states, lambda 1, lambda 2, they are not classical states.
Okay.
In the Brightbone theory, these are variables that are not controllable, for example. You cannot even prepare them.
But it is quantum, right? So it is not. These are not classical preparations, right?
So you're using thin lines here, which I thought.
Yeah, that's right. That's my reading. But you are saying that it is not classical.
Well, in a way, they have to be quantum variables, and
okay.
So here it looks like as if you could prepare that state, lambda 1 psi.
I see.
That's not possible.
That's a very good point, actually.
In the Brightbone theory, so I think the framework might not be as general enough to.
So so we can have a quantum preparation system here, which is controlled by a classical probability distribution. Would that count as?
The problem is that if you were able to prepare the Bohmian configurations, you could do all sorts of.
I see. So you are saying that in principle, I should not draw Bohmian mechanics because I can never know these.
Well, I would say that the status of the variables lambda 1 and lambda 2, they are not of the kind that you wish them to be. They're not classical in the sense that you introduced it. It's ontic variables in the Bohmian framework that behave in a quantum way.
I see. Okay. No. So in these diagrams, we are not claiming that you can prepare all of these things, right? I mean, this may be preparation, that is already there. I mean, it's a very operational definition. It's not about preparing it exactly like this in the lab. So when we are, I haven't started calculating with these diagrams, but when we start doing that, we can keep it as a variable, like a parameter.
Something in your framework.
That was a rather funny thing you just said. That it's a very operational notion.
Yeah.
It's not that we can compare it in the lab. Usually one means by an operational notion that you can do it in the laboratory.
Yeah. No, but, it's there. It's there in the nature. It's not controllable.
Thank you.
But I would love to discuss it further. Sure. Thank you.
Thanks. Could you go back to slide 41 for a moment? I'm not
41?
Sure if 41, I think. I'm not sure if I understood that correctly, but you said that in your diagrams, time moves upwards.
Yeah.
So the discarding of the state essentially happens before anything else. Is that really some interpretational aspect of the process that happens here? Or
yeah, that's a very good question. So you can think of it as a back action because of this discarding. So if you compare these two diagrams, what these diagrams are saying is that if Alice discards her state, it has a back action which affects Bob.
Yeah, in a way that the discarding of the state happens before there is anything else. So is there another way to interpret the last diagram that you've shown?
This diagram. This diagram can also be thought of as preparing a maximally mixed state. That's also, diagrams are by definition, these are they don't come with their own interpretation. The main interpretational aspect that these diagrams are imposing is that, the composition has to be maintained. These connections are to be maintained. That's the only thing that you get from these diagrams.
Okay, thanks.
Thanks. Okay, I guess this is just follow-up, but in that case, the sense in which time is going up seems to be
Ad hoc.
Yeah, because
that's right.
If those two are equivalent, then in one case Alice is discarding first, and then in the second case she's discarding at the end. So time doesn't really go up.
Sorry, say that again.
Well, I mean, in this first equation.
So sorry, I think I should have drawn it clearly. So this is basically when I move this y here, this is Bob's side.
Okay, so Alice doesn't do anything then, really.
I mean, Alice has destroyed her state,
Yeah.
and that is equal to Bob preparing a maximally mixed state.
Okay, but does Alice destroy her state after Bob? Like, you see what I'm saying? Like, before and after seem to be muddled.
Yeah, that's a very good question. So when you are trying to interpret a diagram, you only look at one side of the equation. I can't say that these are like Alice is doing something here and Bob is doing something here, and Alice is also doing something here. I can't say that.
Okay.
No further questions or comments? Okay, great. Thanks a lot, Hamza. Please join me in giving him a round of applause. Thank you.